So yeah, it's 5 minutes after. We're going to hear about Go from Sebastian and Pachyderm from Dan. Sebastian, you're first, so let's all look at your slides.
Okay, so I will start briefly with, so we'll talk about Go HEP and providing robust end-to-end software for HEP. And I will start with a brief software overview of what we get in HEP. So at the beginning of times, we had Fortran 77 till the 90s, and then after the 90s, C++ took roots in HEP, and then starting with the 2000s, we got a bit of Python lurking here and there. But basically nowadays, software in HEP is mostly C++ and Python with a few pockets of Java and Fortran. But having said that, software in HEP is quite painful. First, painful to develop because we have deep and complex software stacks. We have, and at each layer of those stacks, we have huge dependencies, issues. First, to install all of those dependencies, then to support them and maintain them. And because most of our stack is in C++, we have huge compilation time issues. And when we deploy all of that code, we have also issues to deploy those multi-gigabytes of stacks of shared libraries, configurations, and databases. And as a C++ is also a very complex language to learn, read, write, and maintain, this brings its own set of issues. And all of this gives a rather unpleasant edit compile run development cycle. On the development side, and on the user side, we also have well, overly complicated object-oriented systems from the 90s, inheritance hierarchies, meta-template programming. If installing dependencies for the developer was painful, for the user it's also painful. We have also a bit of an issue with the granularity of dependencies. Sometimes we install a huge library just for a couple of functions in the stacks to be used in the stack. Also, there's no real simple nor standard way to handle the dependencies across operating systems, experiments, groups, and of course, well, documentations, but that's not, well, that's a issue throughout the software, I guess. And that's why usually end users tend to prefer Python because of its nicer development cycle, despite its runtime performances. And speaking about the performances, our software is rather painful and doesn't even perform very well because of it's not, I mean, of all of the object-oriented anti-patterns could load from C++ templates and whatnot. They know it's slow to initialize software because of loading all of those gazillions of DPSOs and delays. It's also quite resource hungry to run and develop, both in terms of CPU and VNM and people. And besides, most of our stack has to be rewritten because of multi-core machines and the new implement issue of having the software being parallelized and concurrent. And in my view, C++ 14, 17, or C++ 20 something is rather ill-equipped to address parallel programming and concurrent programming, especially in an environment which is which has to do with distributed development teams and people with very varying programming skills, at least in C++. So you might ask if it's not time for something new. And a couple of years ago, you could put a bunch of programming languages across two axes, having C and C++ on one axis, which is mostly fast and efficient for computers, but not very fast and fun for humans to develop. And on the other axis, you will have Python, Perl, and JavaScript, much more fun to deal with. And of course, well, as I'm talking about Go, you might have seen me coming, and well, Go is, I think, a quite good data point on this previous graph. So what is Go? Well, Go is a rather nice language with with a nice mascot as well. And as for every new language, you have to start with the hello world. And as you can see, well, hello world is rather simple. From this little snippet of code, you can see already that you have a package system because there is this little package keyword. We have also an import system to use third-party language packages or standard libraries, functions, and rather easy on the letter or on the page verbosity as a programming language. And to run Go code or little snippet of code, you just have to use the Go tool, which is named Go, and go on, and then you pass a file which contains Go code, and it will compile and run it on the fly. So a bit of history. It started as a 20% off and on project at Google during, starting with in the 2007 by Grismer, Pike, and Thompson. And it has been released in November 2009, and since then we had more than 700 contributors which joined the project, and now we have a 6-release development cycle, and the next one is slated to be released in this week, probably on Tuesday. So a few elements of Go. So it's a concurrent and garbage collected open source general programming language released under the BSD3 license. It has the feel of a dynamic language because it's really non-verbose thanks to its type inference system. You have also maps and slices, which helps with the, dealing with all of those containers, which we have to deal with. It also has the safety of a static type system, so you don't have a variable which has a type string on line 42, and then a couple of lines later it's an integer. And because it compiles down to machine language, it's relatively fast. The goal is to have across the board runtime performances to be within 10% of C. It's also object-oriented, but without classes. It has also built-in reflection and first-class functions with closures and interfaces which could be compared, described like compiled duck typing a la Python. It's also available on all major platforms, so Linux, Windows, macOS, Android, and iOS, and for many architectures, so AMD 64, ARM 64, i386, and even IBM Big and architecture, and also others. So I don't have much time to describe Go, so I will just give a very couple of slides overview of how the concurrency is managed or handled in Go. So in Go, the concurrency primitives that we have access to are the Go routines and channels, which derive from ROAI's communicating sequential processes, CSP for short. Basically, Go routines are like threads. They share memory, but they are way much cheaper than threads. They can start with a very small segmented stacks, which can grow and shrink as needed. So you can have many Go routines per operating system thread, and you can have many Go routines running and let loose on a program on a very cheap laptop like the one I'm using now. Something that you couldn't do with native operating system threads. So you can have millions of those Go routines. To turn a function into a Go routine, you just have to prepend the DOS keyword instead in front of it, and this will run the function in a Go routine concurrently, but not necessarily in parallel to the other functions or Go routines. And as I said, a Go routine has its own stack, which can grow and shrink as needed. So you don't have a segmentation fault if you didn't compile your C++ program with the needed stack for each thread. Well, that's just a little example on how coroutines are very simple. And just, well, a bit more example. So consider you have a function f, which takes a message string and a delay duration, and then you start an infinite loop, which will just print the message using the standard output, and then sleep for some time, and then print another time that same message and sleep, and so forth and so on. And if you're in your main function, you prepend the call to f with this go keyword, with so first this little a -- message, and then you sleep for 300 milliseconds, and the same for B and C. You have the output of this little program here, and you see that you have well, the three functions running concurrently inside that little program and sleeping at various times. And then after 20 seconds, the program exits. So that's one simple way to execute any function f concurrently to other functions. That's one aspect of concurrency, but you need also communications to be able to transfer information between coroutines and synchronize those coroutines. And this in Go is performed via channels, which are typed conduits, which can well, transport either integers or strings or any type. You can also tag the direction of the channel. So like so, you create a send-only channel, and like so a receive-only channel. So a channel from which you can only well, receive data. Creating a channel is rather simple. I mean, once you have a few hours of Go under your belt. So this little snippet of code declares a new variable ch of type channel of integers. Here you declare and initialize it with the make built-in function, and then you can send an integer to that channel using the left arrow operation and extract this integer data from that channel ch and store it into a new variable x. So channels in Go are a way to synchronize two or many coroutines together by exchanging data. So they are both synchronization and communication activities. So if I go back to my first example, this little f function now takes still the message string, my delay duration, and then the channel through which I will send my data. Instead of printing it directly on the standard output, I just send my message to the channel and then sleep some more. And then the main function it starts with creating a channel through which I will send all of my data. I schedule my three functions A, B, and C, and then I just iterate over the channel 100 times and starts to, tries to extract some data using this little statement. And you can see that indeed I do get all of those, well, indexed messages 99 times if everything is working according to plan. So with this little program, I can have my synchronization and my communications between all of those algorithms. So here I just have the main coroutine, which is synchronized with the three A, B, and C coroutines that you can easily extract to a more complicated hierarchy of coroutines. So well, that's all for this 10 minutes or so introduction to Go. And if you want to have more information, well, you can go to the tour, which is an interactive well, tour of the Go language. And if you are more into concurrency, these two tutorials, talks are really interesting. So what can Go bring for science and HEP? As you may have seen from this 10 minutes introduction, it's a very simple language that anybody can learn and be productive in days and really be an expert in months. I'm not over selling it. You have also a standard tool to handle all of the dependencies across OSs and architectures, and you have really a fast edit compile run development cycle. And, well, many other interesting things. Yeah. So for HEP, of course, you can't really migrate the million lines of code of software already taking data for LHC, so it's not really, well, it's really being optimistic to think that you could switch off all of the LHC C++ software and from day 1 to day 2 go to the Go software stack. So to convince physicists that Go could be useful and usable and viable, I think that the better way would be to tell that, to show off that an analysis in Go is viable and viable and useful and viable. And for this, I started this Go HEP project, where the go-hep.org is where you can find it. And to better exemplify this little project, I started to also work on DAQ and monitoring and control command, and also create a little application for detector fast simulation toolkit, something a la Delphs, to show that it's a nice language. So for the DAQ item, well, for doing DAQ and monitoring and also control command, you need obviously some I/O and some network libraries and obviously some preferences. And Go is a great fit for this. Plus, you have also all of the concurrency building blocks to manage all of that. And at LPC Clermont, I did a bit of that first in the LSST telescope. So I did a little control command plus monitoring application to test one of the sub detector that we have to handle or to construct here in LPC for the LSST, and also a physicist here in LPC did the same thing for a medical application, so a DAQ plus monitoring. But it's not only in LPC that Go is calculating. A team at Oxford for the SOLID experiment also did parts of its DAQ in Go. And now that LPC is also in SOLID, I did also a little application for sensor monitoring in Go, running on a Raspberry Pi. So I started to gather all of these little DAQ HEP-oriented packages under the Whiteback organization in GitHub, and I encourage you to have a look at it. Just flipping some slides about what the GUIs and monitoring application look like of LSST and the medical one. And now, finally, about the fast simulation. So I wrote this little FADS simulation toolkit, which morally is a translation of the C++ Delphs detector simulation in Go. I use a little control framework that I wrote, which is usually the usual event loop to initialize, process, and finalize application, plus some histogramming and HEP input/output. Everything is on GitHub, released under the BSD3 license, and just to show how easy it is to install FADS and usually any Go-based application, we just have, first to export some environment variable, GoPath, which is like the Python path environment variable, which helps the Go tool to locate where to install all of your code and dependencies. And then you just have to say go get and point at some repository. So either a user one or something like GitHub. You point at it and it will retrieve that source code on your laptop if you didn't have it already. Inspect all of the code and recursively download and install all of the packages that your code depends on, and then finally install your library or your executable. All of this without any makefile involved, and this, of course, works with the same syntax and the same semantics on Linux, Windows, or what have you. So, having built my little FADS detector simulation on this little go-hep framework, I have an event-level concurrency and a task-level concurrency. And then as framework relies on the Go runtime to schedule all of the Go routines, the Go runtime has complete and consistent picture of what the concurrency graph is inside your application, even if people are using subtask concurrency level inside their algorithms or modules in CMS speak. So I translated the C++ Delph Atlas Data Card into Go, which I named FADS app, which again can be installed using the same indentation, just giving the full path to the name of the application. And then you have a few options to play with. Basically, this little example has a few components in it. So a HEP converter to be able to read and write HEP events. I did also all of the particle propagation, parameter simulation, a bunch of energy rescalers and momentum sphere, photon, muon, and electron dissolution, debugging, and whatnot, and also an instrument service to be able to look at the results. One thing that I didn't do is implement a very fancier jet clustering. For the moment, I just did the very slow and then the n to the 3 combination scheme that C++ FastJet did. This is just the graph of the dependencies between the tasks and the data object being produced. So I think the square boxes are the tasks and the round boxes are the data products. I did a few test benches on a few servers, I mean Linux and Mac OS servers that I had under my that had available, and I tested everything against Delph's 332 plus this n to the 3 scheme to get everything consistent. And as you can see on this event throughput, where you have the number of threads on the axis and the event rate on the y-axis, that you have already a good scalability, well, up to the 20 or so number of physical cores, and then when you go hyper-threading, it's leveling off a bit, well, a bit, compared to the C++ one, which is obviously single-threaded, and then augmenting the number of threads available to the application doesn't help much. Yeah.
Could I ask about that before we leave this slide?
Yeah, sure.
It looks like there is precisely zero scaling in the C++.
Yes.
Is that because it doesn't have that capability?
Yes. It was just, I mean, I could just have given a flat line without any other points. The C++ Delph's implementation isn't multi-threaded at least with the Delph's 332.
Wouldn't the standard way someone would use that be to run many processes?
Yes.
Okay.
I didn't do that, but of course, if you run multiple Delph C++ processes, you could also run multiple FADS processes. The endpoint being that the C++ Delph's application would be using much more memory as I can show here on this slide. Because this flat line would be, I mean, if you would be multiplying this flat line by the number of processes. Well, at first cut. I would say.
Okay. So now the advantage is more clear.
Yeah.
Okay.
Well, as you can see, the memory footprint of the Go-based application is way better and quite linear too, even with the garbage collector. So just to conclude, well, in this 20 minutes or so talk, I couldn't give you really the impression that Go is really great at doing what we do in HEP. It's really an experience, for lack of a better name, because I must say that the first time I tried Go, I wasn't really impressed, just looking at the tutorials and whatnot. And it was really when I tried on a little on a side project that I was really enthused by the program. And as I said, I came to Go for the concurrency, and I stayed for all of the tooling which is around it, being able to rewrite automatically and refactor a bunch of packages in one command. All of the nice compile edit cycle. It's really great. Of course, for HEP, we still have a few things for Go to be really usable and viable. I'm just listing a few of them here. I think that two of the most important ones are better and more performant root file format interoperability, and I'm working on this with the HEP root IO package. And I must say that right now I didn't push it just before the talk, but I can read T-trees, which are which is really great, at least for me. And we should also have a better integration with Jupyter notebooks. And for this, I know that Daniel is working on Gopher Notes. He's the one who published Gopher Notes, which is a kernel for Go for Jupyter. And having a better integration with plotting and that kind of stuff inside Jupyter would be really great. And yeah, that's basically it. I'm already running past my time. Yeah. Questions?
Not a question, but addition. You mentioned Golang is a garbage collected language, but it's important to mention that actually garbage collector is really fast here. It's nothing like a Java garbage collector. I don't know what the numbers, but it's like tens of milliseconds now to perform actual garbage collecting.
Yeah, with the Go 1.8, there's been rumors of sub-milliseconds pauses even for tens of gigabytes of memory footprints applications. So it's it's a really interesting garbage collector, even if it's still very young compared to the JVM one.
Yes.
Yeah. People on the garbage collector team focused on the latency aspects of the garbage collector rather than focusing on the throughput. And it seems that it's paying off, because you can leverage the latency through throwing many more cores at your application, and by that way getting throughput still. At least that's my very naive understanding of these complicated topics.
Yes, as I understand, we just Go objects, which stores in memory, are much simpler as in other languages, like in Python or Java. So it lets it it enables this fast garbage collecting.
Yeah.
I have a general question, which is, are you targeting simulation, reconstruction, or end users, or combinations thereof? Because from your description of the features of Go, it seems that its simplicity and ease of use is a good target for end users. So we can reduce this let people concentrate on their analyses. But the examples that you were working on are at the simulation end.
Yeah, so historically, as I've been an Athena Gaudi developer, I tried Go with I tried to write a control framework in Go and to see how far it was going, and I was quite pleased, and I tried to push Go like that, but it wasn't a viable way to do it, so I refocused on trying to show that even a control framework like go-hep FWK could be used by a small team of physicists or just a single end user, and still be manageable and have a great development experience. So that's why I started first with the control framework and then reoriented myself towards more end users.
Okay.
And during that migration of focus, there were a few people doing interesting things with the DAQ. So I also branched off with the GoDAC thingy, and I think well, Valentin is also showing in CMS, or trying to show in CMS, that Go can be used in computing too.
Mm-hmm. Yeah. Are there other questions? Okay. So if there are no other questions, let's thanks, Sebastian, and
Sure.
And move on to Dan's talk.
All right, let me try to share the screen here.
Yeah. It often helps to full screen before sharing.
Ah. Oh, looks like I need a Chrome extension.
Well, okay, we won't do it now then.
Okay.
Yeah. So then just call off page numbers.
Okay. All right. So thank you guys for inviting me to talk. It's great to be here. Today I'm going to talk about Pachyderm, which is an open source project that I've been working on for a little bit and interested in for quite a while. I'm a data scientist there, but have a background in physics, as I'll describe, and try to parallel some of those applications. So go to the next slide. Today, I'm going to give a little bit of a story from my physics background that maybe motivates some of the philosophies that went into Pachyderm, and then give you some more details about how data analysis and processing might go in a typical case, and then if I have time, briefly describe one of the research use cases that we've seen, and then hopefully have time for some questions. So go to the next slide.
Page 3.
Page 3. And so I'll describe a little bit, like I mentioned, go to the page 4. And I started out in physics, not in nuclear physics, but I did many-body theory and scattering for my PhD work, and worked a lot in Fortran, doing some simulations, and eventually building in a new feature into an open source Fortran code called Octopus. And in my time doing that, basically I ran into and created some problems for myself. So you go to page 5, I think. One of those was having to do with reproducibility and collaboration. So basically, as my grad work went on, and I was talking to Jim about this beforehand, I kind of created this Wild West for myself where I was doing a bunch of things and writing a bunch of code and trying to name things how I could remember what I did, and arrange my data in a way that I could remember what I did and how to produce the things for the papers that I was writing. And it basically created this scenario in which almost nothing would probably be reproducible for even other people in my group or even myself a month from when I was working on it. So we go to page 6. The other problem that I experienced was having to do with...
Sorry, can I interrupt for a second? Do you want to, do you intend to share the slides, or should one of us share them?
Oh, please do. Please do.
I'm sorry? Yep.
Yeah, just as we were about to share them, it turns out you needed a Chrome extension. Yep.
Okay, so let me see if I can share them, but it's yeah. So go ahead. I'll turn it on in a second.
I think I'm sharing them.
Okay. Can everyone see?
Not yet.
Yeah, there's just a bit of a latency.
Go ahead and do that. Can I get reconnected? We are on page 6 for whoever's sharing. And you should continue.
Okay. All right. Yeah. So the other issue that I was running into in my work was around scaling and parallelization. So basically, I would do certain things for the papers.
Well, I'm sharing now. I don't know about anyone else.
Yeah, I'm also sharing. So
I think Pete's sharing.
I'll quit then.
Go ahead. Sorry.
Yeah, no problem. Sorry for the confusion there. Yeah, so in my work, basically, I would brute force a lot of things and end up writing things like this paragraph saying that, you know, I found densities exactly with finite differences, which if we go to the page 7, basically what the translation of that was, I really didn't know how to make my code scalable, and I, just demonstrated things in a brute force way with a simple solution. So other people that would want to do similar things would definitely have scalability issues. So if we move on now to Pachyderm, as kind of a teaser, for me, Pachyderm really addresses both of these things, both in the context of individual grad students working on projects, but also in the case of larger organizations managing distributed data processing. So if we go to slide 9 and 10, I'll introduce what Pachyderm is. So Pachyderm really aims to help organizations and teams better manage their data infrastructure and their distributed processing. So that's really the goal of Pachyderm. It doesn't really describe what it is. So next, on slide 11, what it is an open source distributed processing and data versioning framework built on containers. So that's a lot of jargon all packed into a single phrase. So let's expand on each of those. So in slide 11, actually 12, yep. So Pachyderm is open source. I'm sure all of you guys know what that means. But if you want to find it, we're on GitHub, and we're an open source project, so all the code you can get. Pachyderm is actually written in Go, so relevant to what Sebastian was talking about, although as I'll describe in a bit, it's language agnostic as far as the types of data processing that you can do with Pachyderm. So moving on to slide 13, it is a distributed processing framework, meaning that you can distribute your processing over a cluster of machines, whether that's running in the cloud or on premises. You can distribute your data between workers and manage tasks like distributed ETL and MapReduce type jobs. Next, on slide 14, it is a data versioning framework. So in addition to providing this capability of doing distributed processing, it provides a file system which allows you to version the data that's coming into and out of each stage of your data processing. This is kind of like Git for data, if you want to think about it that way. So you commit data into Pachyderm, and it's versioned, and those versions are tracked similar to you would track versions of code in GitHub. And finally, slide 15, it's built on containers, Docker containers specifically, if you're familiar with that. I know some of you are working with those. But basically what this allows us to do is to create a language agnostic processing framework. So we can do distributed processing and have this data versioning and have the data processing pieces be in any language or framework that you're used to working in, while still allowing you to distribute that process over a cluster. So that might be in Go, as Sebastian was just talking about. It might be in C++, Root, Fortran, Python. Any of these are possible as long as it can go into a Docker container, and Pachyderm will take care of distributing that processing across a cluster. So moving on to slide 16, I'm going to talk about some example uses of Pachyderm. This will be a simple example, and there is some code that I put up to GitHub that's linked at the end where you can try this on your local machine if you like, but I'll describe it in the slides here. So on slide 17 and 18, let's say that we want what any good physicist wants. We want histograms. And we want, slide 19, we want lots of them for many different experiments or runs, or maybe parameters, conditions, whatever you can imagine. So we want to create lots of histograms based on changing data. So the first thing we want to do on slide 20 is we'll deploy Pachyderm. So Pachyderm itself, it runs on a Kubernetes cluster, which you can think about that as basically an open source way to distribute containers on a cluster. So again, this can run in the cloud or on premises, but if you can have a Kubernetes cluster, which is pretty widely used now, at least in industry, then you can run Pachyderm, and that deploys within a single command. And Pachyderm, the processing, again, it runs in those containers, and those containers are scheduled on Kubernetes. So then next on slide 21, what we would want to do to do some processing in Pachyderm is create a data repository within Pachyderm. So remember, I mentioned that Pachyderm has this file system that takes care of versioning data. And so this repo that we're going to create, this distributions repo, will hold data that we will eventually be plotting in histograms. And that data isn't stored in containers. It's stored in any object store of your choice. So that could be S3, GFS, or on premises something like Menio. Basically, any object store could back this data, whatever flavor of object store you like. So we create this data repository, and in slide 20, we can commit data into that data repository. Again,
22.
Sorry, 22. Yep. Commit data into that data repository, similar to how you would commit code into GitHub. So we would put this file in the data repository, and that might be commit 0. So here I've got one file that I want to convert into a histogram. So that's commit 0. And likewise, I can commit as many files as I want. In slide 23, I have another commit 1 of another distribution file into my data repository. Okay, so that's great. We have data in our repository. And remember, this data is versioned. So at any point in time, I can go back and see what did my data look like at commit 0? What did my data look like at commit 1? What did my data look like at commit 57? So I've got this versioned historical record of what my data look like. So now moving on to slide 24, next I can create a container that converts those files into histograms. So in the example that I link at the end, I did this with Sebastian's tooling in Go. It will take in those files and then produce a histogram. And all I need to do to run this in Pachyderm, again, is to put it in a Docker container. And that Docker container, when I spin this up within Pachyderm, it will create that pipeline. It will also create an output repository where the output of that stage will go. And again, this output repository is versioned similar to the input repository. So in stage 25, on slide 25, what will happen when I spin up that pipeline is Pachyderm will say, okay, I've got this histogram stage that takes as input distributions from this distribution repo, and I can see that I have 2 commits in that distribution repo. So I'm going to push those commits through my stage and update the output. And so in slide 25 and then 26, what Pachyderm will do will be to process both of those files through the Docker container and output the histograms to the output repo. Now, I've just illustrated with 2 files here, but on slide 27, we could commit any number of, any amount and any size of files into here for this processing. So I could commit 1,000,000 files into this distribution repo and have another 1,000,000 commits in my output repo. And what's nice here is that, let's say I commit 2 files initially. Those 2 files are processed and the corresponding histograms are generated in the output. If I then put another 5 files in, I don't have to reprocess the first 2 files because Pachyderm is aware of what's new. Again, it's versioning all this data. So it's aware of what's new, and it will just create the histograms for the new data. So I don't have to reprocess everything. And this kind of this tying of the data processing to the data versioning is really what Pachyderm thrives on, because it keeps your output, your results, in sync with whatever's new coming into your data repositories. So in slide 28, I mentioned that not only is there this data versioning piece and that you can keep your data in sync, it's also a distributed framework. So if you like, you can say to Pachyderm, I would like to split up this processing 4 different ways. And if I committed 1,000,000 of those files in, Pachyderm would only expose 1/4 of those files to each of my workers to process those in parallel. And I don't have to change anything about my code to do that. I keep my same naive code that I wrote before and just have Pachyderm smartly split up the data to do this distributed processing. In slide 29 and 30, I'm just illustrating that, again, this is containerized. So if you don't want to, if you want to do something root related, or if you want to use Python instead, it's as easy as switching out that container. And as soon as you switch out that container, Pachyderm will see that you've updated your pipeline, and it will correspondingly update your results. Likewise, if you would just change the code in that container, Pachyderm can update and keep everything in sync with that updated code. In slide 31, I'm just illustrating something maybe more complicated. So the previous example is simple in that there was only one stage in my DAG pipeline. But I could likewise have stages that take in multiple inputs. I could have multiple stages, and I could have any number of stages. And actually in slide 32, illustrating that any of those stages can be in any different languages. And I can create this pipeline where I have a bunch of different languages all processing data in this pipeline. Each of those stages can be individually scaled or parallelized, as I mentioned before, and the input and output of each of those is versioned. So you know exactly what data was input and output to each stage over time to produce specific results, which we call provenance. So if you create specific results, you can know exactly what data was input and output to create those results. So just briefly, I'm running out of time. On slide 33 and 34, I just wanted to mention a related use case where this team at General Fusion, which is a company trying to commercialize fusion reactor, they're using Pachyderm basically to solve the same problems that I mentioned above. So they had a lot of their physicists pulling down various portions of data from their production environment, analyzing that locally, but then having issues because they didn't have the updated calibrations or the updated parameters. And so what they've done is be able to create a production data pipeline with Pachyderm that keeps everything in sync with their latest calibrations and their latest parameters, and also allowing collaboration because those data scientists or their physicists can pull down the latest versions of their data and know exactly what the provenance was at certain times to produce certain results. So with that, I'll conclude, see if there's any questions. At the end, I did provide some resources on slide 36. We have a public Slack channel where you can just pop in and ask any questions. I'm there at dwhitena. Feel free to ask me questions. Also, there's a link to our docs, and then I link to that simple Go example that you can try locally if you like.
Any questions?
Hi, this is Lucas.
Yep.
Hi.
Looks like this.
Yeah, thanks for the presentation. It looks really great, and it's very similar to what we are trying to develop here at CERN. So I think actually one of the developers from CERN was in touch with you on some of the Pachyderm guys. I don't know how many you are, regarding some Kubernetes detail. So what I'm interested in is how exportable. So I'm interested in the workflow or DAG description language. So what we kind of developed here internally is its own kind of JSON YAML-based language to describe graphs. And so how portable is this? So can I take this pipeline specification and run this outside of Pachyderm?
So the pipeline specification is specific to Pachyderm, but it is in a familiar JSON format. So you can, in the docs, there's a link to the JSON specification. But basically, all it specifies is it says, I want to run this container, so you can specify an image at a certain registry, and I want to run this command, even standard input within the container, and then you say, I want to expose this data to my, or this data is input to my specific stage of the pipeline. So these are these data repositories that I mentioned, and when you deploy that, then it spins up those that pipeline, and when new data comes into those specific inputs, it's aware of that and pulls that image that's specified in the job specification and runs it in the way that you specified, whether that be serial or parallel, and then terminates until there's new data. So in this way, you can basically do streaming and batch sort of things, in the sense that a streaming job is just very frequent commits, where this pipeline will run very frequently, and batch would be less frequent commits.
Okay, so I don't know, maybe we can discuss offline, and I'd be very interested to see how we could hook up the kind of workflow specification that we have into Pachyderm, or whether or not that's even pluggable at all. And
yeah, definitely.
Okay, great. Thanks.
I'd be happy to talk.
Invite me to discussion, guys.
Okay.
Sounds great.
Yeah, you could just do it on the Diane HEP Google group if you want. There may be others who want to join.
Okay, sounds great.
Yeah, that's great. I think I don't have anything to add over what Lucas said, but it is, working on the same sort of project is definitely has a lot of commonalities, and it's nice to see. And definitely the sort of prov and then the data tracking part of it is nice. I like that.
Thank you. Yeah, I'd be very interested to hear about the similarities with your guys' projects and possible ways to help each other and provide some feedback as well.
Any other questions? Because so we're at
great.
time. Yep.
I have to sign off, but thank you. Bye.
Yeah. Okay. Thank you.
I want to thank both speakers for keeping on schedule. How unusual. Also, really good presentations.
Thank you.
Thanks.
Okay. So if there's no other questions, then I guess we'll meet next week.
Okay, bye.
Okay. Bye. Bye-bye.
Bye.
Do we have a meeting scheduled for next week?
We do. That one is next week, the 27th.
No.
No, not quite. Ah, then we'll see you in 2 weeks.
Okay. Thank you.
Okay.
Hey, Jim, do you want to maybe stay connected? I don't know what your schedules are.
We could do that.